In this video, we're going to go through a carbon dating model example. First, a little background. In living organic material, the ratio of the content of radioactive carbon isotopes, or carbon-14, to the content of non-radioactive carbon isotopes, carbon-12, is about 1 to 1012. When organic material dies, its carbon-12 content remains fixed, whereas its radioactive carbon-14 begins to decay with a half-life of about 5,700 years. To estimate the age of dead organic material, scientists use the following formula, which denotes the ratio of carbon-14 to carbon-12 present at any time t in years. We call this the carbon dating model. So we have R equals 1 divided by 10 to the 12th times E raised to the negative t divided by 8,223. So here the graph of R is shown in figure 4.26. Note that R decreases as t increases. So let's do an example. So here the ratio of carbon-14 to carbon-12 in a newly discovered fossil is R equals 1 over 10 to the 13th. So we want to estimate the age of the fossil. So we're going to take 1 over 10 to the 13th and put that in the R's spot. And we're going to set that equal to 1 over 10 to the 12th times E raised to the negative t divided by 8,223. So from here, we're going to multiply both sides times 10 to the 12th to get that 10 to the 12th to go away. And that's going to give us, because there's 10 to the 12th on the top and 10 to the 13th on the bottom, there's going to be 1 10 left on the bottom. So 1 over 10 equals E raised to the negative t divided by 8,223. To get the t out of the exponent, we're going to take the natural log of E, or of both sides rather, and we're taking the natural log because our base of the exponent was E. So the natural log of both sides enables us to cross out the natural log and the E on the right side, leaving us with the natural log of 1 over 10 equals negative t divided by 8,223. So we're trying to solve for t, so we're going to multiply both sides by a negative 8,223, which will allow us to cancel out the negative 8,223 in the denominator on the right-hand side. So we're going to be left with negative 8,223 times the natural log of 1 over 10 equals 10. So simply plugging that into our calculator gives us a value that t is going to be approximately 18,934. So what does that tell us? Well, that tells us that the fossil is about 19,000 years old. Let's take a look at a Gaussian model. Remember that our Gaussian model is y equals a times e raised to the negative x minus b quantity squared divided by c, and is a bell-shaped curve. Now, this type of model is commonly used in probability and statistics to represent populations that are normally distributed. So the standard normal distribution take the form of y equals 1 divided by the square root of 2 pi times e raised to the negative x squared divided by 2. The average value for a population can be found from the bell-shaped curve by observing where the maximum y value of the function occurs. The x value corresponds to the maximum y value of the function, represents the average value of the independent variable, in this case x. We're going to do an example to kind of illustrate this a little bit better. So in 2013, the Scholastic Aptitude Test, or the SAT, mathematics scores for college-bound seniors roughly followed the normal distribution of y equals 0.0034 e raised to the negative x minus 514 quantity squared divided by 27,848, where x was equal to or between 200 and 800. So x is the SAT score for mathematics. We're going to use a graphing utility to graph this function and then estimate the average SAT mathematics score. So we'll pull up our graphing calculator and we're going to go ahead and put in our equation 0.0034 times e raised to the negative x minus 514 quantity squared divided by 27,848. Now remember the x needs to be between 200 and 800, so we're going to need to adjust our window a little bit. So we'll open up our window and let's make our y minimum let's see, x had to be between 200 and 800. So let's make it 150. Oops, that should be 150. And let's go up to 850. And let's count by 100. For our y minimum, let's say it's square of 0, and let's go up to 600, and let's count by 50s. So go ahead and we'll hit graph. And as we look at this, we see that, wow, we can't really see anything, so maybe our window isn't set where we need it to go. So another option we have is to go to zoom and arrow down to fit, which is option 0, zoom fit. And if we hit that, we'll see it pull up. And if we check our window to see maybe where we went wrong, we see that our y's were just much too large. So here we had basically from 0 to 0, but the window is 0.00002 to 0.003. So pretty intense there. Let's go back to our graph. And because we're looking for our maximum value, we're going to calculate our maximum using the calculate feature of our graph. So second trace will bring up our calculate feature, and we want the maximum value. So we need to be on the left side of our maximum, and then we're going to move over to the right side of our maximum and make sure that our maximum is between our two lines, and hit enter. And we're getting an x value of approximately 514. So let's go ahead and write that down. So here we have that maximum score of 514. Now a little something to help you also, so if you didn't want to do the zoom fit, another way we could have known what our window needed to be is if we looked over here in our problem, it said 0.0034. So that's kind of a hint that we're going to need some smaller numbers. 0.0034 is our y maximum. And so we needed numbers that were really small. So that's a clue to kind of help you get those values. So here we're able to say that the average score in 2013 was a 514.